Hello engineers, welcome back. In this video, we're going to solve an optimization problem using dynamic programming. I hope you're ready. Let's get started. So in this video, we will see the question coin change. Okay, we've already seen this question during our greedy method discussions, but in this video, let's try to solve it using dynamic programming. So let's try to understand the question and then we'll build the solutions. So you're given an integer array coins representing coins of different denominations and an integer amount representing a total amount of money. Return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up by any combination of the coins, return -1. Okay, so let's try to understand this with this example. So let's say our coins are 1 to 5 and amount is 11. So coins, available coins are 1 to 5 and amount is 11. So how do I make 11 with these coin types? So I can do it like this: 5 plus 5 plus 1 will give me 11. I can also do 2 plus 2 plus 2 plus 2 plus 2 plus 1. This will give me 11 as well. And there can be so many combinations. Okay. So in greedy method, we thought we will use the largest denomination first and then the second largest and so on until we reach the amount, and we have written that solution. So greedy amount may not work for every possible coin type, because let's say the example 3 4 5 2, let's take not 2 1. Okay, and amount can be 7. So I can make 7 using 5 plus 1 plus 1, which is a greedy method. First use the highest amount of element, highest denomination, and then keep checking forward, and then you end up with 5 plus 1 plus 1, which is 7. But this is not the minimum number of coins, right? I can also make 7 with 3 comma 4, which is 2 coins. So greedy method may not work in every possible situation. That's why we can use dynamic programming in this case, so that we can explore all possible combinations and check whichever is the minimum. I will return minimum coins from here. Okay, so how do we do this? So first let's build the recursive solution. So my amount is 11, which means to pick the first coin I have 3 choices: 1, 2 and 5. So I can either pick 1 rupee coin, I can pick 2 rupee coin, I can pick 5 rupee coin. If I pick 1 rupee coin, the remaining amount will be 10. If I pick 2 rupee coin, remaining amount will be 9. If I pick 5 rupee coin, remaining amount will be 6. And we can repeat this process. If I keep picking 1 rupee coins, I can go to 9, 9 will go to 8, 8 will go to 7, 7 will go to 6, 6 will go to 5, 5 will go to 4, 4 will go to 3, 3 will go to 2, 2 will go to 1, 1 will go to 0. Now here we can stop. This is our target, which means we have found a valid path to reach our target. From here we can return 0 because there are no more coins to take, and this will be our base case. And if there is an invalid path, for example, I am at 1, from 1 I can choose to make three possible choices, right? I can pick the 1 rupee coin, I can pick the 2 rupee coin, I can pick the 5 rupee coin. Okay, this is an invalid path because 1 minus 2 will give me -1, 1 minus 5 will give me -4. So this is a valid path. These two are invalid paths. So whenever the current amount is less than the coin itself, then we don't need to pick that, right? You cannot make 1 rupee with 2 rupee coins. You cannot pick 1 rupee with 5 rupee coins, right? That doesn't make any sense. Okay, so there are valid paths and there are invalid paths. Okay, and I am interested in not the number of paths, but I am interested in the fewest number of coins. Okay, so how do we get that? So this is a valid path. There is only one valid path here, and this will return 0 for me because it is a valid path. And if it is an invalid path, we can choose to return -1 from both of these situations. So if it is an invalid path, return -1. Okay, these will be our conditions for stopping the recursion. Okay, now among these three, there is only one valid path. So if I find a valid path, I can choose this coin. I can possibly pick this coin. If there are no valid paths, I don't need to pick it. I can return -1. Right? So in this case, I have found one valid path so that I can pick this coin. So I will return 1 here. There is one coin I can pick. Now let's see this from 2's point of view. From 2's point of view, there are three choices, right? One is the 1 rupee coin. I can also pick the 2 rupee coin. I can also pick the 5 rupee coin. If I pick the 1 rupee coin, I know that this is a valid path. So this is one possible solution. And if I pick the 2 rupee coin, I will end up with 0, which is again a valid solution. If I pick 5 rupee coin, 2 is less than 5, which means this will end up being negative, which is an invalid path. Okay. So here there are two valid paths. First valid path is returning 1 to me, and the second valid path will return 0 to me. Okay. From 2's perspective, there are two valid paths, 1 and 2. One is returning the value 1, 2 is returning the value 0. I am interested in the minimum path. So I will compare these two. Whatever is minimum is 0. So I will add this coin. This coin is now valid, right? Because there is at least one possible path. So I will add this coin to the minimum coins list and I will pass on 1. I will do 0 plus 1. If I go down this path, I don't need any more additional coins. I will just use this coin and I will return it. If I go down this path, I need one additional coin. So that would have become 2 coins. So 1 coin and 1 coin. 1 rupee plus 1 rupee will give me 2 rupees. So I will return 1 here. Let's look at it from 3's point of view, just for our better understanding. From 3, we have 3 choices again. This is the first choice, going down the 1 rupee road. This is the second choice, going down the 2 rupee road. And this is the third choice, going down the 5 rupee road. Now we know this is an invalid case because 3 is less than 5. Now here 3 is greater than 5. So we can go down this path. Here there is 1. 1 will again call on 3 things, 1, 2, 5. We know that this is a valid path. This is an invalid path. This is also an invalid path. So from 3 as well, there are two valid paths, right? So first valid path is going down the 1 rupee route. If I go down 1 rupee route, I need to take one additional coin. If I go down 2 rupee route, let's see what happens. So I'm going down 2 rupee route, 2 is calling on 1, will return me 0, and which means this is a valid case. This will return me 1. Okay. So in both these cases, I am getting 1. So it doesn't matter which one I choose. I can just pick this coin and add it up and pass on 2 here. So one coin from here and one coin from here. Both are same. So we have found our minimum number of coins, and we will pick this coin because there is a valid path, and we will pass on. And this process repeats until we reach the end. And then when we reach here, this will again make those choices. 6 will again make those choices, and so on. Okay. So this is the recursive case. So what is the time complexity here? As you can see, every coin, every amount is making 3 additional coins here. So because we have 3 coins here, every amount is making 3 additional coins, which means uh, there are 3 calls here, there are 3 calls here, 3 calls here, 3 calls here. So this is 3 to the power of amount, 3 to the power of 11 in this case. So if we generalize it, it is the size of coins dot size to the power of amount. So this is the time complexity of the recursive solution. Okay, so let's try to code it and see how it goes. So we'll build our recursive solution. So first let's make a function which is called get min coins, and we will take our vector of coins and the amount. So whatever recursion we want to do, we'll do it here, and whatever that function is returning will be our answer. So we will pass in coins and amount. Okay, now let's see what do. We do the base case first. What is the base case? If amount equal to 0, then return 0, because minimum number of coins required to make the amount 0 is 0. If amount is less than 0, which means we have found an invalid case, then return -1. Okay, now let's build the recursive case. Okay, so in our previous study where we discussed climbing stairs problem, at every n we had two choices, right? I can make one step or I can make two steps. The choices were two and they were fixed, so we used direct recurrence relation. But here the number of choices is dynamic. Here there are three choices, here there is only one choice, here there is only one choice. Okay, so we need to explore all choices. So for that we will use a loop. For int I equal to 0, I less than what, coins dot size I plus plus. So this is our exploratory loop. Inside this loop we'll call recursion. Okay, so what do we call? We are obviously passing the coins vector, and at every case we are reducing the amount, right? So let's say we are here, we have chosen the first coin, and what will be the next input? It will be 11 minus 1, 10. Okay, so that's what we'll do here. So amount minus coins of I. Okay, now this will give me a result. Now I need to make use of this result. So how do I do that? Let's go down the recursion tree, because this is where return starts. If I find 0, which means I have found a valid path. If I find -1, which is an invalid path, I'm not interested in this. So let's eliminate that. If result not equal to -1, okay, then this is a valid path. Now I need to keep track of minimum coins. So let's keep a tracker. Int min coins equal to, let's call it int max for now. Let's give it a huge number and we will compare it with our current result. Let's say I got my result 0 here, which means this is a valid path, right? So I will add one coin to the minimum number of coins required. So first I will check if the current result is less than the already available minimum coins, then minimum coins equal to result plus 1. So here I'm getting the result 0, which means I can use this coin. Here I'm getting the result 1, which means I can use this coin. So 1 plus 1 will give me 2. Here I can give 1 and I can use this coin, so 1 plus 1 will give me 2, and so on, right? So I'm maintaining a track of minimum number of coins. After I've explored everything, which means we are here right now, and I've explored 3 paths, and I know the value in min coins. Right? Here I need to do a check. If min coins is still int max, which means after exploring all 3 paths, if it is still int max, which means there is no possible path here, then I will return -1 because the question said. Okay. Otherwise, I will simply return minimum number of coins. Okay, and that's it. Try to run and see. Our recursive case is accepted, but will it be enough for every possible? Obviously, the answer is no, because time limit exceeded for an amount of 100. Obviously, because when there is a huge number, the tree becomes large and large, and eventually we will reach time limit exceed. Okay, so now let's optimize. How do we optimize? We know that we can use 2 methods. One is memoization, and the other one is tabulation. So how to use memoization? Memoization we have discussed before. If you haven't seen my other video, please go and watch Introduction to Dynamic Programming. So what do we do? Memoization solves the problem of overlapping subproblems, right? So you can see here, I'm calling 9 here, and 9 is getting called here as well. 6 is called here, and 6 is getting called here as well. So this is overlapping subproblem. So to avoid this, we keep track using a DP vector of size n plus 1. Here in this case, n is amount, so we can keep track of amount plus 1. We'll go from 0, 1, 2 all the way up to amount, right? And at each step, I will store the solution, which means if I know the solution to 1, I will go here and update the value here. The solution is 1 is returning 1, right? I will store 1. So 0 is 0, and so on. And I can use this DP array to make a DP check. If DP of amount is not equal to -2 or 3 or whatever, so I would have initialized all this with -2, let's say. And if it's not -2, I can use the solution from here, right? We have already seen this. So let's use that. So this will reduce the recursive calls. So let's create a DP vector. Let's call it DP. Size is amount plus 1. And we will initialize it with -2. Here we will introduce the DP check. So first we need to pass the DP. Here we will take the DP vector as a by address. We need to pass DP here as well. Now we can use the DP check. If DP of amount is not equal to -2, which means there is already a solution available, we will use DP of amount. Otherwise, we have to store the result. So we will store instead of returning, we will store DP of amount equals -1, and here DP of amount equal to min coins, and we will return DP of amount. Okay, and that's it. Let's run and see. We made some mistake. Let's put this in the else block. And we can run it now. Submit. So now our solution is accepted, right? So we have used memoization to reduce the number of recursive calls. Now, what is the time complexity of this? So the time complexity of this is the amount, whatever is the amount, into the size of coins, or we can say coins dot size, because we are no longer calling the problems that are already solved. So we are calling this many times. So we go down this path and we call it 11 times, and here we call it 3 times, and that's it. So this will be the size of coins, and we use this path to make linear calls. So that will be the time complexity using memoization. It will be same for tabulation as well. So now let's see the tabulation method. Okay. So for tabulation, we know that we create a DP vector again, and we will start filling it from bottom up. So this is a bottom up approach. Memoization was top down. We started at the top and we have eliminated unnecessary recursive calls. In tabulation, we will use bottom up, which means we will start filling this array from 0 all the way up to. So the size of this will be amount plus 1. So how do we fill it? So the first one is dp of 0. We already know the answer to this because when we reach 0, the number of coins required to make the amount 0 is 0. So we can directly put it here. What about the remaining values? We can initialize this dp vector with the max values, int max, right? And we will use the recurrence relation to get the values of each dp index. Okay, so let's see how we can get dp of 1. For dp of 1, we need to explore 3 paths, right? This is the first path, this is the second path, this is the third path. So let's say I'm exploring the first path. So we have 3 paths, 1, 2, 5. So this is the first path. So currently we have max in our dp vector. I need to check this path, and if I find a solution, I will check with this. Whichever is the minimum among these two, I will replace it here. That will become the solution of dp of 1. Okay, so minimum of current dp value, current dp of 1 with the path that I want to take. Path is here. This path will be obtained by doing dp of 1 minus 1. Okay, because dp of 1 minus 1 is here. We are here. dp of 1, if I do 1 minus 1, I will end up here. Right? This is what we need. And we already know the answer to this. It is 0. Okay. So this is dp of 1, which is carrying the value of max. And this is dp of 0, which is carrying the value of 0. Right? Max with 0. But I know that this is a valid path, which means when I'm giving the solution to 1, I can pick the current coin, right? That's what we did here. When I know that it is a valid path, I am using that path, whatever is the minimum coins from that path, plus 1, because I can now use the current coin. So I can do plus 1 here. So that will be the relation. So 0 plus 1. So what is the min of max and 1? The answer is 1. So my dp of 1 will be. So let's do another example so that it is more clear. How do I get dp of 2? For dp of 2, again I need to check 3 paths, right? I'm checking the first path now. The first path is min of dp of 2, current dp, with dp of 2 minus the first path, minus 1, 1. I know that dp of 2 minus 1 is a valid path. Only if there is a valid path, I will come down this route. Okay. So what is dp of 2? It is max currently. And dp of 1, which we have just calculated, dp of 1 is 1. So 1 plus 1 will give me 2. Max of these, max comma 2, what is the min of these two? Min of these two will give me 2. So I will replace it here. But am I done? No. I need to check additional paths as well. So I will go down the second path. What is the second path? Min of dp of 2 and dp of 2 minus 2, second path, plus 1. I know that this is a valid path. So what is dp of 2? Current dp of 2 is carrying the value 2. dp of 2 minus 2 is 0. dp of 0 is 0. 0 plus 1. So what is the min of 2 comma 1, which is 1? So I will write my answer. So the dp of 2 is carrying the value 1, which means the minimum number of coins required to get the amount 2 is 1, because I can use the 2 rupee coin. Okay, so we can use this relation to build our tabulation. So let's see. So let's remove all this. So don't need this. dp vector is there. This time I will initialize everything with int max. I will initialize it with max and I will get the minimum value. So how do we fill it? First one is simple. dp of 0 is 0, right? From 1 onwards we will fill it using a loop. Int I equal to 1, I less than or equal to amount I plus plus. And for each I need to check each coin. So I will use an inner loop. Int I equal to, let's call it j equal to 0, j less than coins dot size. We are checking each coin, and j plus plus. Now I am filling dp of I. So in order to fill dp of I, first I need to check whether that path is valid or not. How do I know whether that path is valid? Let's see. So when I'm at 1, if I go down the value path 2, I know I will end up with negative value, which means whenever I am choosing a path which is greater than the current amount, it will be an invalid case. So I need to avoid that. So if I is greater than equal to coins of j, if my coin is less than my amount, only then I can go in. And another condition is it should be a valid path, which means I should have already solved it. If I'm here 2, if I want to go down this route, if I go down this route, I need to know that this has already been solved. Only then I can use the relationship, right? Because we are using the concept of optimal substructure, which means there should be some relationship between the current past solution with the previously solved solutions. Okay. So I need to know whether this has already been solved. From 1, I need to know whether this has already been solved. So I can use that check. So dp of I minus coins of j. This value should not be int max, which means it is already solved. Okay. Now I can fill my dp with the relation that we have seen here. Minimum of current dp value with the current coin I minus coins of j. And because I know it is a valid path, I need to return one more coin, okay, to store in my solution. And that's it. So now I can simply return dp of amount. Okay. Let's run it. We made some mistake. Okay, we are directly returning the dp amount, but we need to make a check whether after doing all this calculation, if we don't find any solution, then we need to return -1, right? So we check here. If dp of amount equal to -1, sorry, int max, which means we have not found any solution, then we will return -1. Otherwise, we will return dp of amount. Now let's run it. So our solution is accepted. So what is the time complexity? As you can see here, first loop is going all the way up to 1 to amount. This is the operation amount. And the second loop is going from 0 to coins dot size. So that's what we saw here. Amount into coins dot size. Same thing applies to tabulation. So in this question, we have used three approaches: recursion, memoization, and tabulation to solve the question using dynamic programming. Okay. If you have any questions, you can definitely ask me. Thank you so much for watching. Don't forget to leave a like and subscribe to the channel if you haven't already. And don't forget to bookmark the playlist so that you don't miss out on a future video. And thank you so much for watching, guys. I'll see you in the next one. Cheers.